magnetic properties, right? Magnetic properties of materials. So magnetic properties, all materials won't exhibit magnetic properties. Only certain materials exhibit. We'll see what are the conditions and what are the materials. All right. Magnetism, the phenomena by which materials assert an attractive or repulsive force or influence on the other materials. So you know, magnetic force is either a metal should attract another one or it should repulse, right? So one of these two possibilities are there. Has been known for thousands of years, right? So this we all know that. Okay, this is a phenomena. However, the underlying principles and mechanisms that explain the magnetic phenomenon are complex and subtle, and their understanding has eluded scientists until relatively recent times. So the phenomena behind that, how only some materials are attracting, why some are not attracting, so these kind of phenomena still under discussion. Many of our modern technological advisors rely on magnetism and magnetic materials. These include electrical power generators, transformers, motors, radio, television, telephones, computers. So these all are dependent on the magnetism, you know, right? Motors, they need temporary magnet, right? Electromagnet. Television, telephones, right? So these all need this magnetic property, right? Iron, some steels, and the naturally occurring mineral lodestone are well-known examples of materials that exhibit magnetic properties. So you know, iron and some steels usually they exhibit magnetic property. Not so familiar, however, is that the fact that all substances are influenced to one degree or another by the presence of magnetic field. So this presence of magnetic field, there are chances that they are getting magnetic attraction, but the strength is different, right? The strength is varied. So this chapter provides a brief description of the origin of magnetic field and all about the magnetic field, right? So we'll see basic concept. Magnetic dipoles, right? Magnetic dipoles. Magnetic forces are generated by moving electrically charged particles, right? So you know, usually magnetic fields are generated by moving an charged particle through a current flux, right? Or electric flux. These magnetic forces are in addition to any electrostatic forces that may prevail. Many times it is convenient to think of magnetic forces in terms of fields, right? So magnetic field, usually we call it as magnetic field, you see. So these are magnetic fields. Imaginary lines of force may be drawn to indicate the direction of the force. So magnetic dipoles are found to exist in magnetic materials, which in some respects, not respect, that expect, are analogous to electric dipoles. So when you see here, yeah, right, this diagram, so this usually you know, right? So magnetic field exhibit from north to south. So field lines start from north and will end up in south, right? So they will go like this all the way around and ended up in here, right? So this is a magnetic field lines. Magnetic field lines of force around current loop and bar magnet, right? So this is bar magnet and this is current loop, okay? Right, magnetic fields in a manner similar to the way in which electric dipoles are affected by electric fields. Within a magnetic field, the force of a field itself exerts a torque that tends to orient the dipoles with the field, right? So if you have a material that will tend to insert a torque on this direction. A familiar example is the way in which a magnetic compass needle lines up with the Earth's magnetic field. So if there is an already available magnetic field, which is Earth magnetic field, you know the compass will also take that particular direction. Magnetic field vectors. So we will discuss this formula first. We describe magnetic behavior in terms of several field vectors. The externally applied magnetic field, sometimes called as magnetic field strength, that is this H, right? So H, the magnetic field strength, if the magnetic field is generated by means of a cylindrical coil or solenoid, right? So you know what is a solenoid is. Solenoid is something like this, okay? This is what called as a solenoid, all right? Cylindrical coil or solenoid consisting of n closely spaced turns. So this n is the number of turns here, 1, 2, 3, 4, 5, like this, right? Number of closely spaced turns having a length L. So this length is the L, right? This length is the L, and carrying a current of magnitude I, right? So this conductor should have carrying a magnitude of I current, right? Then a schematic diagram of such an arrangement is shown in the figure 20.3a. So clear this, and I'll go to that drawing. Yeah, here we have that, right? So this is what called as a solenoid, okay, which is carrying a current of I, right? This I is passing through this and coming out by this way, and the length of the solenoid is given as L, right? Then length of the solenoid is given as L. So the magnetic flux generated, it is H, right? When you put this into formula, H is equal to N into I upon L, right? So the magnetic field strength H is equal to N, that is number of coils, into I, that is current, the magnitude of the current, divided by L, that is length of the conductor, right? Length of the conductor. The magnetic field that is generated by the current loop and the bar magnet is an H field. So here the field is H. The unit of H are ampere turns per minute, so per meter. Ampere, I is ampere, N is turns per length is given in meter, right? So unit is simple. Ampere, I is given in ampere, turn is given, N is given in turns, and L is meter. So the unit is ampere turns per meter, or just amperes per meter. Magnetic induction of flux density denoted by B represent the magnitude of the internal field strength within the substance that is subjected to an H field. Right, so this WB is known as Wegener, right? Both B and H are field vectors being characterized not only by magnitude but also by direction in space. We will study this H, right? So this equation we will study, right? So first we will see this one. So here current is going this way, okay, and the total length of the coil is this much, right? So due to that, the magnetic field generated is H, okay. The magnetic field H is generated by a cylindrical coil, is dependent on the current I, right? So how much is the current passing through is a dependent factor. A number of turns N, right? So number of turns. So when the turn increases, the magnetic field strength increases, right? When the current increases, the strength increases, and with the coil length, that will decrease. The magnetic flux density B naught is the presence of vacuum is equal to mu naught into H. Yeah, mu naught is the permeability of the vacuum. Magnetic flux density B within a solid material is equal to mu H. Yeah, mu is the permeability of the solid material, and mu naught it's in the vacuum, right? There's a mu naught. Where's mu naught? Yeah, here. This mu naught is the permeability in the vacuum. So this equation is for field strength within the material, right? Within the material. This H is created due to the current passing around the material, right? That's the difference. So here this B represent the magnitude of the internal field strength within a substance that is subjected to an H field, right? So if it is subjected to a magnetic field H, the internal field is given by B, right? Internal field is given by B. The unit of B is Tesla or Webers per square meter, right? We'll either put it as like T capital or WB per meter square. Both B and H are field vectors being characterized not only by magnitude but also by direction in space, right? So when you see, everything has a direction. So current is going by this way, coming by that way, field strength is going that way, right? This is going this way. So everything has a direction, right? Everything has a direction. Magnetic flux density B, right? This is magnetic flux density B, and this is magnetic field H. Two are different things. Within a solid material is equal to mu into H. So B is equal to mu into H, right? B is equal to mu into H, where we'll see what is this mu is, right? B is the presence of a presence in a value vacuum is equal to mu naught h, right? So this mu is a variable. If it is vacuum, it will take mu naught. If it is some other material, that will take mu, which is a value, right? Where mu naught is the permeability of a vacuum, that is 4.10⁻⁷ h per m, right? 10⁻⁷, you see the value, right? Flux density B within a solid material, right? So now it's not vacuum, it's a solid material, is equal to mu h, right? That is mu h, where mu is permeability of the solid material, right? So here the mu is the permeability of the solid material. So parameter mu is called as the permeability, which is a property of specific medium through which the H field passes and in which B is measured, all illustrated in this figure, right? So here permeability is the property of specific medium through which the H field passes. So to pass these fields need a medium and in which B is measured, right? The permeability has dimension of Webers per ampere, that is WB per AM or Henrys per meter, HM also we can say. In the same case, while in vacuum, that is B naught is equal to mu naught into H. Same equation, if it is a solid material, that will take B is equal to mu H. When in a vacuum, that is V naught is equal to mu naught into H, right? Mu naught into H. Where mu naught is the permeability of a vacuum, a universal constant, right? So this one is the universal constant, which has a value of 4.10⁻⁷. Okay. So this is the terms related to magnetic flux density and magnetic field strength.